Hello and welcome to the Theory of General Relativity Simplified, where we unravel the wonders of general relativity without drowning in equations. I'm your leader through this journey, Jennifer, and today we're taking our very first step into the world that Einstein reimagined over a century ago. If that sounds daunting, don't worry. It's also mind-bendingly cool. Gravity is the quiet choreographer behind every step we take, every leaf that drifts to the ground, and every planet that circles a star. It's so woven into the fabric of our daily lives that we scarcely notice its presence. Yet it underlies the shape, motion, and destiny of everything from galaxies to coffee cups. Let's begin our tale in the late 17th century with the man of the hour, Sir Isaac Newton. He was the rock star of physics long before the term rock star existed. Newton's law of universal gravitation came from his insight that the same force pulling an apple toward the Earth also keeps the moon orbiting above us. This concept was radical in the 17th century, and it gave humanity its first unifying law that described both earthly and celestial motion. Newton's equation for gravitational force is elegant. The force between two masses is proportional to the product of those masses and inversely proportional to the square of their distance. For centuries, he was revered as the greatest mind in science. But for all the genius behind Newton's law, it was incomplete. It worked beautifully for most everyday phenomena, but by the early 1900s, scientists were picking up on tiny discrepancies that Newton's framework couldn't fully explain. The orbit of Mercury, for one, kept playing hard to get with Newton's predictions. Over time, these small cracks hinted that maybe the universal force wasn't so universal after all. In 1905, a young Albert Einstein was working in a Swiss patent office, but also tinkering with ideas that would reshape physics. It was this year when he wrote 4 groundbreaking papers in one miracle year. But the real fireworks came a decade later in 1915, when Einstein published his theory of general relativity, revealing that gravity wasn't a mysterious force pulling objects. It was the result of curved spacetime. For over 200 years, Newton's story of gravity had been the sacred text. And now someone comes along and says, that invisible force? Actually, it's not a force at all. But Einstein had conviction. His new equations perfectly explained Mercury's funny orbit. And soon, scientists sought more ways to test this radical new viewpoint. That sets the stage for our topic today: how Einstein's theory reframed gravity as geometry itself. Before we can tackle Einstein's grand view of gravity, we have to rewind a few years to the groundwork he laid in 1905 with special relativity, because that's where the concept of space-time was first crystallized. In the late 19th century, physicists wrestled with electromagnetism and the perplexing discovery that light's speed was constant for all observers, no matter how fast they were moving. Picture yourself in a spaceship racing toward a beam of light. You might expect that light would approach you faster than if you were standing still. Yet experiments such as Michelson-Morley ether experiment and Maxwell's equations revealed that no matter what you do, light still blazes along at about 300,000 kilometers per second. No more, no less. This baffling fact led Einstein to propose 2 radical postulates in special relativity. First, the laws of physics are the same in all inertial frames. That is, if you're moving at a constant velocity, the usual physics still applies. And second, the speed of light in a vacuum is constant for all observers. Those simple statements forced us to abandon the idea of absolute time and absolute rest. Instead, Each observer measures distance and time based on their relative motion, which can differ from someone else's measurement. From these postulates arose the phenomenon of time dilation. If you're traveling at speeds close to light, your clock will tick more slowly compared to someone who's standing still. Meanwhile, your spaceship might see the other person's clock slow down from your vantage point. Relativity is symmetrical in that way. This mutual time dilation is mind-boggling, but repeated experiments, like flying atomic clocks around the world, have confirmed it. Another outcome is length contraction, along the direction of motion. Distances shrink for the moving observer. If you're zipping near light speed, a 100-meter stretch of road might appear to be only 50 meters. Even more bizarre, events that happen simultaneously for one person could occur at different times for another. This is known as the relativity of simultaneity. So how do we make sense of this new world without absolute time? The short answer is that space and time aren't separate at all. They're two threads woven into one seamless fabric we call spacetime. Picture it like this. Instead of having a big room called space with a giant universal clock somewhere else, Einstein realized those ideas had to merge. 3 dimensions of space and 1 dimension of time all blend into a single 4-dimensional stage where events play out. When you move, you're actually traveling through both space and time, and someone else moving at a different speed or direction might split those 4 dimensions differently. That's why each observer ends up with their own perspective on what's simultaneous or how long something lasts. No one gets the final say on an absolute timeline. There isn't one. It all depends on your motion. This 4-dimensional viewpoint also keeps the speed of light consistent for everyone, which is what experiments demanded. Since space and time are just aspects of the same fabric, any change in one affects the other, ensuring light's speed never wavers. In everyday life, these differences are small, but when we talk about high speeds or strong gravity, the effects become dramatic. Clocks can slow down, lengths can shrink, and events you thought happened together may not be simultaneous for someone else. In short, space-time is our new backdrop, a single unified way to think about distance, duration, and motion, all at once. Special relativity handed us this surprising revelation, and it transformed the question of gravity from what force pulls objects into how does mass reshape the geometry we all move through. That's where general relativity steps in. We can think of each observer as moving on a personal world line through space-time. Their notion of now, past, and future depends on their motion. Minkowski, one of Einstein's contemporaries, famously said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." But special relativity has a boundary. It handles situations where observers are moving at constant speeds or are far from gravitational influences. The moment we introduce acceleration or significant masses like stars, planets, or black holes, special relativity doesn't have the final word. After all, special means it's limited to inertial frames only. The second you have to deal with a rocket blasting off or you're standing on Earth's surface feeling pulled downward, you're no longer in an inertial frame. Einstein realized that a deeper theory was needed to handle acceleration and gravity. One of the first major hints that something was wrong with the classic physics view of gravity came from the orbit of Mercury, which refused to follow Newton's laws to the letter. Its closest point to the Sun, the perihelion, kept shifting slightly more than predicted by classical equations. Astronomers tried to patch this by inventing a hidden planet named Vulcan or by tweaking Newton's formulas, but none of that stuck. Similar small discrepancies appeared in the Moon's orbit around Earth, and efforts to unite gravity with the then emerging field of electromagnetism were fraught with contradictions. By the early 1900s, these clues had piled up enough to suggest that gravity, as Newton defined it, needed a deeper explanation. By 1907, Einstein had begun wondering, what if gravity and acceleration are actually the same phenomenon at heart? This led him to the equivalence principle, the idea that free fall under gravity is indistinguishable from inertial motion in empty space. If you're in a tiny elevator, you can't tell whether you're being pulled down by gravity or accelerating upward. That insight cracked open the door to general relativity, where the geometry of spacetime itself would play the starring role. In essence, special relativity tells us that time and space flex with motion, but it stays silent on what happens when mass and gravity enter the scene. That's where general relativity comes in. Einstein set out to describe not just how objects move when traveling at high speeds, but also how they move when massive bodies warp the fabric of spacetime. The result would turn our notion of forces upside down. If this introduction to special relativity feels fast, don't worry. Check out our series dedicated to special relativity, where we go deep into the wonders of Einstein's genius. So, to understand how Einstein defined gravity as geometry, picture a large, stretchy trampoline. Imagine that the trampoline's surface represents the fabric of space-time, when nothing massive is around, so it's perfectly flat and at rest. Place a bowling ball in the middle and watch the fabric sag. That bowling ball stands for an object with mass, like a planet or a star, causing the once flat surface to bend under its weight. Now, roll a marble across that sheet, it curves around the bowling ball. While the marble wants to move straight ahead, but the sheet beneath it is no longer flat. It slopes downward toward the bowling ball, so the marble's straight path in this curved environment ends up looping around. If you were to look at it from above, you'd see the marble tracing what appears to be a curve, almost like it's being pulled by some force. We tend to say the marble is attracted by a force, but you can see there's no actual pulling hand here. Instead, the marble's just following a straight line in this newly curved surface, what physicists call a geodesic. In other words, there's no invisible pull, it's simply traveling along the curved path in the stretched fabric. This captures the essence of Einstein's insight. Mass changes the geometry of space-time around it, and any smaller object naturally follows that geometry. You might remember from school geometry class that the shortest distance between 2 points on a flat surface is a straight line. On a sphere, however, like Earth, the shortest route between two cities is along a great circle. We call that the sphere's geodesic. According to Einstein, when you see a planet orbiting a star, it's not spinning around from some force. The planet is traveling on a geodesic in 4D space-time. Because that space-time is curved around the star, the path loops around. In 3D, it looks like a circle, or ellipse. In 4D, it's a straight shot. To take Newton's example, the apple falls not because of an invisible hand, but because it moves along the local geodesic, which plunges it toward Earth's surface. This geometry doesn't just affect the space part. Time itself gets tangled in it. Have you ever wondered if your watch and someone else's watch can tick differently, purely because of where you stand on Earth? This revelation leads to gravitational time dilation, the phenomenon that deeper in a gravitational well, clocks run slower compared to those far away. It's not science fiction. It's built into your phone's GPS and confirmed by countless experiments. Imagine living at sea level, where gravity is slightly stronger, versus living atop a mountain where it's slightly weaker. The difference is small, but measurable. Did you know that time doesn't actually flow at the same rate everywhere? It turns out that if you stand on a mountain peak and compare watches with someone at sea level, you two won't agree on the length of a second, at least not exactly. This mind-boggling fact is a direct result of gravity's ability to warp not just space, but time itself. In physics speak, we call this gravitational time dilation. Sound wild? It is, and it's also extremely well tested in labs, airplanes, and even inside your phone's GPS. So buckle up, we're about to explore how gravity can alter the very flow of time. In Einstein's General Relativity, mass, like that of Earth or the Sun, curves the fabric of spacetime. Instead of a force pulling you downward, objects follow what's known as a geodesic, the straightest path in a curved four-dimensional world. But if space can be curved, time can be curved too, because space and time are interwoven into a single entity called spacetime. Gravity's deeper consequence is that clocks run slower the closer they are to a massive object. In other words, time itself becomes dilated. The effect can be tiny or huge, depending on the mass involved and how close you are to it. Imagine two people with extremely precise clocks. One person stands near sea level, deep in Earth's gravitational well. The other stands on a tall mountain. From the viewpoint of the mountain dweller, the person down at sea level is in a stronger gravitational field, and thus their clock ticks slightly slower. If both individuals reunite and compare watches, they'll find a slight discrepancy. Time literally passed at different rates for each of them. This phenomenon is known as gravitational time dilation. Stronger gravity, slower clock, from the standpoint of a distant observer. At everyday altitudes, the difference is minuscule, but it's measurable with modern atomic clocks. Over cosmic scales, like near a black hole, these differences can become extreme. The movie Interstellar probably did the most famous demonstration of the concept of gravitational time dilation. As the Endurance crew lands on a seemingly tranquil, water-covered world, we are introduced to the idea that gravity doesn't just pull on objects, it also warps time itself. Orbiting perilously close to Gargantua, a supermassive black hole whose immense gravity bends space-time, the planet becomes a stage where 1 hour equates to 7 years back on Earth. While that world was fictitious, the gravitational time dilation is as real as it gets. So, setting the movie aside, how do we know that gravitational time dilation is true? One of the earliest experiments that attempted verification of gravitational time dilation was in 1959 at Harvard, known as Pound-Rebka. Physicists Robert Pound and Glenn Rebka Jr. placed a gamma-ray source, using the Mossbauer effect for extreme precision, at the bottom of a tall tower in the Jefferson Physical Laboratory and a matching detector at the top. By carefully measuring the gamma ray's frequency shift as they climbed upward and then descended downward, they found that photons lost a tiny amount of energy when moving against Earth's gravitational field, an effect known as gravitational redshift. In essence, light emitted from lower in the tower arrived at the top with a slightly lower frequency, consistent with time running slower, deeper in the gravitational well. But, arguably, the most famous tests of gravitational time dilation, and of Einstein's broader relativity, unfolded in 1971 as the Haufele-Keating experiment. Physicists Joseph Haufele and Richard Keating procured 4 cesium beam atomic clocks, each capable of measuring time so precisely that even a microsecond's drift would stand out. They then boarded commercial airliners and flew around the globe, 2 clocks traveling eastward to westward, while a reference clock stayed put at the U.S. Naval Observatory. Why subject these clocks to jet-lagged world tours? Because, at high altitude, gravity is slightly weaker, which would speed up a clock according to General Relativity's predictions. Meanwhile, the airplane's velocity would introduce special relativistic effects that tend to slow the clocks down. The big question was whether the measured differences would line up with what Einstein's equations forecast. By the time the clocks returned, each had gained or lost time in precisely the manner Einstein's theory dictated. The eastward flying clocks lost a bit of time relative to the reference, while the westward clocks gained time. A direct confirmation that motion and gravity both shape the flow of time. It was a landmark moment, reported in the journal Science in 1972. Suddenly, the notion that clocks could disagree based on altitude and speed wasn't just a blackboard hypothesis. It had crossed over into the real world on everyday commercial flights. If you're wondering, why should I care? The answer might be in your pocket. GPS satellites orbit about 20,200 kilometers above Earth, where gravity is weaker than it is on the surface. As a result, their onboard clocks tick slightly faster from the perspective of someone on Earth. But the satellites are also moving at high speed, which, via special relativity, causes their clocks to tick slower. Combining these two competing effects means an average satellite's clock gains around 38 microseconds per day compared to clocks on Earth. While 38 microseconds doesn't sound like much, without correcting for it, GPS location data would drift by kilometers daily. Engineers designed the GPS system to compensate, making gravitational time dilation an integral part of how your phone accurately shows you the nearest coffee shop. We've seen how clocks actually run at different rates, just from changing altitude or traveling on planes. So what's behind this weird effect? Einstein's big leap was to show that gravity isn't really a force, it's what happens when mass alters the shape of spacetime. Think of Earth's mass as creating a sort of slope or bowl around it. If you're deeper in that bowl, say at sea level, you're in a stronger gravitational region, and clocks there tick more slowly compared to clocks higher up, on the bowl's rim. Einstein's equations formalize that slope or bowl into a precise structure. In particular, for a round, non-rotating planet or star, the Schwarzschild metric is the mathematical description of how distances and time intervals get stretched by gravity. You don't need to memorize the formula. Just picture it as a recipe that says, the closer you get to the planet's center, the more time slows down. This is the same framework that explained Mercury's off-kilter orbit, let us predict that GPS satellites would need time corrections, and gave us the confidence to run experiments like Hafele-Keating. On Earth, the bowl is shallow, so the slowdown is tiny. But near extreme objects, like neutron stars or black holes, time can slow to a crawl compared to an observer far away. While the effect is small at Earth altitudes, maybe a fraction of a microsecond difference per day, modern technology like geolocation, satellite communication, and fundamental physics experiments rely on this understanding. Even the U.S. National Institute of Standards and Technology has demonstrated that raising or lowering an atomic clock by mere centimeters can yield measurable changes in ticking rates. So yes, it's real. If you're in your basement, time runs a hair slower than if you're in your attic. Not enough to keep you young forever, but enough for a good dinner party factoid. If gravity can bend time in such small ways around Earth, what about truly extreme environments, like near black holes or neutron stars, where gravity is crushingly intense? Could time virtually stand still from an outside viewpoint? Indeed, it can. To fully understand just how bizarre it gets, we need a deeper dive into the language of curved geometry that Einstein used. Riemannian geometry. Imagine a world where straight lines aren't so straight. Triangles can add up to more than 180 degrees, and space can swirl in ways your middle school geometry teacher never mentioned. Welcome to Riemannian geometry, the living, breathing mathematics of warped surfaces and curved spaces. In Einstein's universe, geometry doesn't just outline shapes. It morphs beneath our feet and shapes the paths we travel. Surfaces can ripple and bend, angles can add up all weird, and the fastest route between 2 points might defy every flat map you've ever seen. For centuries, geometry meant Euclid. Euclid's postulates told us that parallel lines never meet. Angles in a triangle sum neatly to 180 degrees, and a straight line was always the shortest path between 2 points. That's all true, if you stay in a perfectly flat world. But our real cosmos had a surprise up its sleeve. It isn't perfectly flat, and that's where some brilliant minds like Carl Friedrich Gauss and Bernhard Riemann step onto the stage. Gauss was measuring large-scale triangles on Earth's surface to see if geometry might differ from the standard rules. He suspected Earth's curvature would produce small deviations. Meanwhile, his student Bernhard Riemann took the idea further. What if we applied this curvy geometry to spaces beyond just Earth's 2D surface, to higher dimensions or even 4D spacetime? Riemann proposed a radical generalization that set the foundation for what Einstein would later use in general relativity. Picture yourself standing in a huge open field, everything perfectly level. If you start walking in a straight line, you never deviate. Parallel lines remain parallel, and the angles in a triangle will add up to exactly 180 degrees. That is your classic flat plane, the arena of Euclid's geometry. It's comfortable, predictable, and doesn't offer many surprises. Now imagine instead of a flat field, you're standing on a giant sphere. If you try to walk in what feels like a straight line, you'll circle around and come back to your starting point, because straight on a curved surface means something else entirely. Triangles drawn on this sphere can have angles summing to more than 180 degrees, and lines of longitude that you'd call parallel at the equator end up meeting at the poles. We call that positive curvature. Everything bends outward, so to speak. Finally, think of a saddle shape, the kind you might see on a horse. This shape has a hyperbolic or negative curvature, and geometry there can be even wilder. Triangles can sum up to less than 180 degrees, and so-called parallel lines can slide away from each other, messing with your sense of straight ahead. These three examples, a flat plane, a sphere, and a saddle, illustrate the major types of curvature where distances, angles, and straight lines can change drastically once the surface bends. And that's just in 2 dimensions. Now, stretch your imagination to include one more dimension for time, and you begin to see why Einstein declared that space and time form a unified fabric, which can warp around a mass. Our beloved circle or ellipse might look curved in 2D space, but in the bigger 4D picture, it's actually the straight line or geodesic. To tackle that, we need more than everyday geometry books. We need Riemannian geometry. Now that we've seen how surfaces can bend in mind-boggling ways, the natural question is, how do we even discuss a shape that's curving all around us, even in extra dimensions or in space-time itself? That's where Riemannian geometry takes center stage. It equips us with a language that extends the flat concepts of distance and angle to wildly curved realms. At the core of that language is the notion of a manifold, which lets us treat seemingly complicated surfaces, or even 4D space-time, as if they're locally flat but globally bent. A manifold is basically a shape that can be locally flat but globally curved. Think of Earth's surface again. If you walk around a small patch, it seems flat under your feet, but if you travel around the globe, you realize it's a sphere. Similarly, space-time is a 4D manifold. Locally, physics can feel very Newtonian or normal, but across larger distances, and especially around massive objects, the shape curvature becomes apparent. That's why an orbit that looks elliptical in 3D can be seen as a straight line in 4D geometry. Now that we're on a manifold, we need a rule for measuring distances and angles. That's where the metric tensor comes in. Think of it as the instructions you follow to figure out how long something is, or how big an angle is, at each point on the manifold. In a flat world, the metric stays the same everywhere. No matter where you go, distances and angles behave identically. In a curvy world, the metric can vary, reflecting how local geometry is stretched or squeezed. This means at higher latitudes, for example, where angle changes, distances measure differently than near the equator. This local measuring tape approach allows you to handle everything from a gently sloping hill to the intensely curved region near a black hole. So, who keeps track of how your measuring tape warps as you move around? That's where the Christoffel symbols and curvature tensors step in. Think of Christoffel symbols as a built-in GPS for your coordinates. They tell you how to tweak your directions when moving from point to point on a curved manifold. If space were perfectly flat, these symbols would be zero, meaning no adjustments are needed. But if you're on a sphere or a saddle, or near a massive star in space-time, these symbols light up, telling you, hey, your directions are changing here. Then you have curvature tensors. These are like the master logs of how bent your manifold is. The Riemann curvature tensor is the full record, describing bends in every possible direction. Meanwhile, the Ricci tensor zooms in on the part that matters for Einstein's equations, telling us how volume or area elements might change under gravity. The scalar curvature is just one number at each point that says, overall, how curvy is this region? Put simply, Christoffel symbols handle the local steering adjustments, while curvature tensors handle the grand shape of the manifold. And yes, it sounds fancy, but in practice, it's just a way of saying we have a system for tracking how your environment warps distances, angles, and directions. Legend has it, when Bernhard Riemann delivered his inaugural lecture on the foundations of geometry in 1854, he was extremely anxious. Gauss was in the audience, and Riemann was presenting an idea so radical, extending geometry to arbitrary dimensions and shapes, that it sounded outlandish for the mid-1800s. Gauss, however, was impressed. That lecture would eventually set the stage for everything Einstein needed to describe the gravitational field. Finally, let's connect this to actual motion in curved spacetime. A geodesic is the manifold's version of a straight line. On a sphere, geodesics are great circles that might seem curved on a 2D map, but are locally the most direct route. In 4D spacetime, a geodesic is the path an object follows when no other force, beyond gravity, acts on it, meaning it's free falling. If you drop an apple or launch a satellite, you're watching objects gliding along geodesics in Earth's spacetime curvature. That's why Einstein could say, gravity isn't a force, it's geometry. Mercury's orbit near the Sun is a geodesic shaped by the Sun's stronger curvature, explaining that extra precession Newton missed. Locally, a geodesic might not appear that dramatic. Zoom in on Earth's surface and it feels flat. Zoom in on a small region of space-time and you might not see the curvature. But across vast distances, you'll notice that your straight path leads you in a loop, offsets your orbit, or changes angles in surprising ways. That's the difference between local normalcy and global weirdness in a curved manifold. We've explained how you can measure curvature, how to define straight lines in a bent environment, and how Mercury's orbit or an apple's fall is just geometry in action. But we still haven't tackled how mass makes space-time curve in the first place, or how to find the exact shape of that curve for a given mass distribution. That's where Einstein's field equations come in. The blueprint that ties mass energy to these curvature tensors and geodesics, telling them exactly how to shape the cosmos. If you've spent enough time involved in conversations about relativity, you've likely heard the phrase, mass tells spacetime how to curve, curved spacetime tells mass how to move. While that might sound like a neat slogan on a t-shirt, it's actually the entire theme of general relativity bottled into one sentence. The field equations embody exactly that cause and effect structure. In essence, these equations tie together two major pieces. The first is mass energy distribution. It refers to the idea that every form of energy or mass in a given region of space-time can be accounted for and logged. In Einstein's theory, it's not just mass in the everyday sense. Any form of energy, like electromagnetic radiation, pressure inside a star, even momentum of particles, contributes to how space-time is curved. Because general relativity sees any energy content as capable of bending space-time, the field equations need a complete tally so that no matter what sort of energy or mass you throw in, space-time's curvature responds accordingly. The second is that the curvature of space-time is essentially the idea that the very geometry, all the distances, angles, and straight lines in space-time changes in the presence of mass or energy. Imagine space-time as a flexible fabric. If a massive object sits on it, the shape of that fabric around the object bends inward. Things passing by, like planets or light beams, then move as though they're traveling on a sloped or dented surface. When you put them side by side, you get something that says, wherever there's more mass or energy, there shall be more curvature. Einstein's field equation can be written as involving the Einstein tensor, the stress-energy tensor, the cosmological constant, and the Einstein gravitational constant. It looks complex, but no need to panic. Let's break down each symbol in everyday language. Let's start with the left-hand side, the Einstein tensor. Think of it as a compact summary of how space-time is curved. We know from previous discussions that curvature means distances, angles, and geodesics don't behave the way they would in a flat world. But to predict orbits or gravitational lensing precisely, we need a single mathematical object that combines all those aspects of curvature into one coherent measure. The Einstein tensor is exactly that. It's built out of more fundamental curvature quantities like the Ricci tensor and scalar curvature, and does two big jobs. First, it tells us how volumes or areas might get squeezed or stretched, imagine a rubber sheet, in different regions. Second, it ties that local squeezing/stretching effect to the geometry at every point, ensuring consistency across the manifold. In short, the Einstein tensor is the geometry side of Einstein's equations. Next up is cosmological constant and the metric tensor. Cosmological constant is essentially a term that can act like a uniform energy density spread throughout all of space-time. Imagine the entire universe has a built-in background energy that isn't coming from stars or planets, but from space itself. When that happens, the equations show a sort of push, similar to an anti-gravity effect, that can drive the universe's expansion. The metric tensor is the blueprint for measuring distances and times. Think of it like a blueprint or set of instructions that tell you how to measure things, distances, angles, even durations of time, at each point in your space-time fabric. In the actual universe, where space-time can curve around massive objects, those measuring instructions, i.e. the values of the metric tensor, vary from place to place. That means a meter near a black hole might not correspond to the same meter out in the emptiness of interstellar space. When multiplied, these terms effectively add a universal push or pull, possibly driving cosmic acceleration. If cosmological constant is 0, you get a simpler set of equations. If not, you might have a runaway expansion like dark energy. Einstein originally added this term to keep the universe static, but later called it a mistake. Yet modern data suggests it might solve the riddle of an accelerating cosmos. Moving to the right-hand side, we see a set of universal constants that keep the equation balanced. It includes Newton's gravitational constant from classical gravity, the speed of light, and, well, pi. The fraction ensures that when we measure mass or energy, we convert it properly into geometric curvature. Finally, we have the stress-energy tensor, that cosmic ledger we introduced earlier. It tracks everything from the density of matter to the flow of momentum, from electromagnetic fields to pressure in a star's core. In other words, if you have more matter/energy jammed into one spot, the stress-energy tensor spikes there. It's a whole table of how energy and momentum shift in space and time. It's multi-dimensional, telling you not only how much energy is present, but also in which direction it's moving or pressuring. Putting it all together, and in simpler terms, the equation claims that the bending of space-time, left side, is something proportional to the energy and momentum present, right side. If you have 0 matter/energy, no cosmological constant, then space-time might remain flat or follow simpler vacuum solutions. If you throw in stars, black holes, or cosmic inflation, the equation modifies the geometry accordingly. The reason this equation is so critical is because it unifies all gravitational phenomena under one umbrella. Instead of having separate theories for orbits, star formation, or cosmic expansion, we use a single equation that says mass energy is geometry's driver, geometry is mass energy's stage. It's a neat cause and effect dance, all spelled out in one line of algebra that's surprisingly short, yet unbelievably broad in scope. Each symbol and the constants plays a distinct role, capturing geometry, uniform vacuum effects, measuring rods, cosmic currency conversions, and energy distributions. Combine them, and you get the simplest yet most profound statement. Gravity is geometry, shaped by what's inside the universe. So how do Einstein's field equations explain some of the strange phenomena we observe in the universe? Delve deeper, and you discover entire classes of weird predictions. scenarios that might seem ripped from science fiction, yet come as a result of varying assumptions in the field equation. Black holes, white holes, and collapsing geometry. Perhaps the best-known bizarre solution is the black hole. Solve the field equations for a massive object collapsing under its own gravity, with minimal pressure or rotation, and you get an event horizon, a point of no return, plus a central singularity where density shoots toward infinity. That single solution, the Schwarzschild metric for non-rotating, or Kerr metric for spinning black holes, is fully spelled out by the same piece of mathematics that explains Mercury's orbit. And if you thought black holes were strange, think again. There is something even weirder than a prediction that comes out of field equations, namely white holes. White holes pop out if you reverse time in certain solutions. You get a region where matter can only exit, never enter. It sounds unphysical and no one's observed one, but again, it's the unaltered equations that predict it if you allow those symmetrical boundary conditions. Then we have gravitational waves and ripples in reality. In a flat Newtonian world, space doesn't undulate. Yet in Einstein's math, if you let two massive objects, like black holes, spiral into each other, the field equations show that their changing stress-energy distribution sends out traveling waves in spacetime. These ripples are no more than the geometry adjusting to violently changing mass configurations. The fact that we've actually detected these waves with LIGO proves that the equation's more exotic solutions aren't just abstract. The geometry does flex and vibrate like a cosmic trampoline. Field equations also present the mind-bending possibility of negative mass, or negative energy. If you assume some exotic form of stress energy, the stuff on the right side of the equation, the geometry on the left side can respond by forming bizarre curves that lead to hypothetical phenomena like repulsive gravity. We don't know if such matter or energy can exist physically, but the math under Einstein's rules is flexible enough that if it did, geometry would get even stranger. Think warp drives or stable wormholes. Next up is the tantalizing possibility of a wormhole. Wormholes are hypothetical tunnels in space-time, possibly connecting distant regions or different universes. If they exist, they might allow near-instant travel, though none have been empirically observed yet. Nothing in the fundamental structure of the field equations automatically bans a wormhole. Basically, a handle or shortcut bridging two distant points in space-time. The simplest wormhole solutions often require negative energy to keep them open, which is why we call them exotic solutions. If we discovered a real form of negative energy material, the equations say a traversable wormhole might be stable, potentially allowing for shortcuts or time travel paradoxes. In short, these phenomena aren't add-ons or separate theories. They pop out from the exact same equation. All that changes is the content. What kind of energy distribution you assume, the boundary conditions or the initial setups, like an imploding star or a hypothetical negative energy region. The geometry side, the left-hand terms, then dutifully reshape spacetime to match, producing everything from gravitational waves to wormholes. That coherence is why Einstein's equations have reigned supreme for a century. They unify the everyday and the bizarre under one universal law of gravity as geometry. Which bizarre scenarios actually exist out there is a question for astronomers, gravitational wave observers, and future experiments to test. But the fact that a single line of math can handle black hole collisions, cosmic expansion, and hypothetical warp drives is a testament to the broad power of Einstein's field equation. Instead of layering new force laws or gravity modifications for each new phenomenon, one equation can generate them all, if you let it. Albert Einstein was an extraordinary mind who reshaped our understanding of space, time, and light itself. Before even reaching the age of 40, Albert Einstein had already overturned centuries of Newtonian physics with his theories of special and general relativity. His contribution to photoelectric effect earned him a Nobel Prize. He is arguably the greatest physicist of the 20th century and definitely the most famous. From proving the photoelectric effect to predicting how starlight would bend around the sun, Einstein's track record of correct, even radical, predictions seemed almost superhuman. Yet Einstein was still a mortal man, shaped by his time and sometimes trapped by his assumptions. For all his genius, he couldn't prevent something that he called his greatest blunder, the cosmological constant, from his field equations. It's difficult to overstate how deeply people in the early 20th century believed in a static, unchanging cosmos. While some speculated on infinite or cyclical universes, the consensus among astronomers and physicists was that the overall layout of stars and nebulae was roughly stable. There was no reason to suspect an ongoing expansion or contraction. Enter Albert Einstein, fresh off the triumph of General Relativity, published in 1915. Within that new framework, matter and energy warp space-time, causing objects to follow curved paths. The Einstein field equations do precisely that, relating spacetime's shape, left side, to the distribution of mass energy, right side. To put it simply, on one side of the equation you have the geometry, which sums up how space is bent or stretched. On the other side is the energy, which details where matter, radiation, or momentum reside. The equation means that wherever you have more mass energy, you get more curvature. But if you plug a large-scale distribution of matter, like all the stars in a galaxy, into Einstein's equations without any extra modifications, you typically find solutions that collapse inward or expand outward. Anything but static. Einstein, along with most astronomers of his day, couldn't imagine a dynamic cosmos. He famously wrote in 1917, "To the question of the distribution of matter, the theory can give no answer." But he tried to force a solution to keep the universe static. To force a static model, he introduced a small fudge factor on the geometry side, a repulsive ingredient he hoped would perfectly balance gravity. He called it the cosmological constant, denoted by the Greek letter lambda. That added piece acted like a uniform repulsion across all of space, counteracting gravity's inward pull. If tuned just right, Einstein believed it would hold the cosmos in perfect equilibrium. But this fix came with a price. It felt ad hoc, even to Einstein. He justified it, though, by the conviction that the universe shouldn't be evolving on large scales. After all, who'd observed anything else? Fast forward to 1929, astronomer Edwin Hubble, working at Mount Wilson Observatory, measured the redshifts of numerous galaxies. He found a clear trend. The farther away a galaxy is, the faster it recedes from us. This correlation, now known as Hubble's law, implied that space itself was stretching, carrying galaxies apart. This revelation sideswiped the static universe assumption. If everything's zipping away from everything else, you don't need a cosmic force to keep matter from collapsing. Indeed, you might not want it. The field equations without lambda already predicted an expanding or contracting cosmos. So, from Einstein's new vantage, lambda looked superfluous. Upon learning of Hubble's findings, Einstein reportedly said adding lambda was his biggest blunder. Later accounts vary on the exact phrase, but the sentiment sticks. In a letter to Georges Lemaitre, who'd independently discovered an expanding universe solution, Einstein confessed he should have believed the mathematics of general relativity from the start rather than cling to a static ideal. He recognized that by introducing cosmological constant just to freeze cosmic evolution, he'd missed the chance to predict universal expansion outright, a huge missed opportunity. So, for decades, cosmological constant was considered a historical footnote, an unnecessary patch on Einstein's otherwise immaculate equations. Yet history had a twist in store. In the late 1990s, two teams of astronomers, the High Z Supernova Search Team and the Supernova Cosmology Project, studied distant Type 1a supernovae standard candles that let us measure cosmic distances and the rate of expansion. They expected to see the universe's expansion slowing down due to gravity, but instead found the supernovae were dimmer, implying they were farther away than expected. That spelled accelerated expansion. Suddenly, cosmologists realized a small, repulsive term might be fueling this runaway. The simplest candidate to fix equations was Einstein's old friend or enemy, the cosmological constant. Suddenly, cosmological constant soared from defunct to explanatory hero, credited for 70% or so of the total energy content of the cosmos, under the new label of dark energy. Further data from the Cosmic Microwave Background, CMB, and large-scale galaxy surveys reinforce the idea that, along with matter and radiation, the universe holds an extra uniform energy component, behaving just like a cosmological constant. Observations fit a concordance model of about 5% ordinary matter, 25% dark matter, and 70% dark energy, with dark energy acting essentially like cosmological constant. So, was Einstein's biggest blunder actually his greatest insight? Maybe. But as we'll see, calling cosmological constant exactly the final word has its own complications. One major interpretation is that cosmological constant represents vacuum energy, a quantum phenomenon where even empty space teems with fluctuations. Trouble is, straightforward quantum calculations predict a vacuum energy way higher than what we observe, like 10 to power 120 times too large. That difference between theoretical predictions and real data is sometimes called the worst theoretical prediction in the history of physics. So if dark energy equals vacuum energy, why doesn't it blow the universe apart at warp speed? Physicists have no crisp explanation yet, prompting many to call this the worst fine-tuning problem in modern science. In response, some propose quintessence, a dynamic field that changes over time unlike a simple constant, or phantom energy, which might even accelerate the expansion so violently it rips the universe apart in a big rip. These ideas come from playing with the form of the stress-energy distribution in the field equations, tweaking the dark energy side to act more flexibly than a static cosmological constant. Whether these theories stand is an open debate. They do highlight that a simple cosmological constant might be too static or too fine-tuned. Observations so far, though, remain consistent with a cosmological constant, at least within current precision. More recently, refined measurements of the expansion rate via supernova data and local distance ladders versus data from the early universe, like the CMB, yield two different values for the Hubble constant. This discrepancy, dubbed the Hubble tension, has reignited speculation. Maybe the dark energy evolves or interacts, or maybe new physics modifies the standard cosmic recipe. Again, we're forced to wonder if plain cosmological constant can carry the day, or if something more subtle is afoot. Einstein's regret primarily stemmed from his refusal to trust the equations when they implied a non-static universe. If he'd embraced that solution, he might have predicted cosmic expansion years before Hubble. Instead, he injected cosmological constant to force stasis, only to discover the universe didn't want to sit still at all. Hence blunder, a fix that overshadowed a more revolutionary revelation. On top of that, once Hubble's law exposed expansion, Einstein realized cosmological constant had lost its original purpose. That double whammy, overriding a correct result, then adding an unneeded constant, stung enough for Einstein to publicly disown cosmological constant. Fast forward to 1998, and astronomers hail a small cosmological constant-like term as the key to cosmic acceleration. A cosmic irony if ever there was one. Had Einstein stuck to no cosmological constant, he'd have predicted expansion. But ironically, if he'd kept an extremely small cosmological constant, he might have foreseen an accelerating expansion. In reality, neither path played out, and we're left marveling at how this blunder now shapes 70% of the cosmic energy budget. Is it truly a blunder if it turns out to explain the biggest puzzle in cosmology? Well, Einstein wasn't wrong that adding cosmological constant for a static universe was misguided, but modern science resurrected it for entirely different reasons. In that sense, his initial use was indeed flawed, but the constant itself can't be dismissed. So, do we live in a cosmological constant-dominated universe, or do we have some evolving form of dark energy? Observationally, a simple cosmological constant still fits the data well enough, though the Hubble tension and quantum vacuum mismatch remind us we might be missing pieces of the cosmic puzzle. Meanwhile, alternative theories swirl from quintessence fields to phantom energy. The field equations can handle all of them, provided we specify the right stress energy form, hence the diversity of models. From upcoming supernova surveys to gravitational wave observatories that might detect subtle changes in cosmic expansion, the quest to nail down cosmological constant versus alternatives rages on. Einstein may have called cosmological constant his biggest blunder, but modern physicists rely on it to explain why galaxies are racing away from us faster and faster, billions of years into cosmic history. Was it truly a blunder or not? That might be for the future to decide.